That's a couple of things to talk about. So what do we have? We have a track that is made of neodymium iron boron magnets. So these are the strongest permanent magnetic material that we know. So I mean, you can't tell with your fingers, but basically they are lined up so that these little tiles have a north and a south face. So if the inner track's all north, the middle track's all south, and the outer track is all north. And this just helps us with the second piece of flux pinning that I'll talk about in a minute. It just gives it a bit more stability. Inside this train that I'm going to use in a minute, I have two black discs, right? These are yttrium, barium, copper oxide. So it's a high temperature superconductor, and it has a transition temperature of about 93 Kelvin. So what that means is that it will go superconducting if I put it in liquid nitrogen, which is boiling at the lower temperature of 77 Kelvin. Okay? But at room temperature, they're pretty boring materials. They're not magnetic. You can see there's no reaction to the magnets here. You know, they're black, a little bit like coal. Really not much to see. But we'll see how they change their properties when we cool them down in a minute. So I'm going to cool them down with some liquid nitrogen. So, you know, there's a little bit of safety needed to talk about here. Can we have a lot of fun with liquid nitrogen, make ice cream and stuff like that, right? But, you know, imagine a liquid that is 200 degrees above room temperature rather than 200 degrees below it. They're really bad burns. And likewise, you know, our bodies aren't adapted to getting into contact with this kind of stuff. So we have to treat it with a bit of respect. You know, there's various different ideas around the safety that you should have in handling liquid nitrogen. Some people do say wear gloves, but other people would argue that, you know, if you're wearing a glove and it gets soaked in liquid nitrogen, now you're holding all that cold very close to your skin. For small splashes, what happens is the nitrogen almost evaporates instantaneously. It doesn't have a large heat capacity. So, you know, small splashes won't actually do you any harm. So it might be better then, if you're only anticipating a small splash, to not use gloves because they're not building up all that cold close to your skin. That's what I adhere to, but the safety office actually prefers people to wear gloves. And, you know, that's probably, you know, if you do the safety course on nitrogen, then you should probably adhere to that while you're using it here. So actually, maybe I should do that too, just to be a good citizen. I'm not anticipating much in the way of splashes. I'm going to put some safety specs on too, so I don't get any in my eyes. Again, I'm not anticipating that a small splash in my eye would do me any harm anyway. What else to say about it? It has some sort of unique properties. When it spills on surfaces, you might see it in a minute, it forms these little bubbles. So has anybody ever put water into a hot frying pan? You know, it forms those little bubbles and they skate around on a sea of their own vapor. So in terms of this surface compared to the temperature of the liquid, you know, this is like a red hot frying pan compared to the temperature of that. And so nitrogen, you'll see, does exactly the same thing. It's a little bit less dense than water, so it tends to skate around a little bit more quickly. I'm just going to put some nitrogen into this container so it's a little bit easier to pour. All right. So it's minus 200 degrees, so you can just pour it. Right, a lot of it boils away. And you can see that on it's a fairly humid day today, so we see a lot of that water vapor as well. So I've got some in there. Got quite a full cup actually. I don't know if you can see that. And I can maybe just stand back a little bit and spill a little bit on there. So you can see all the little droplets, right, all skating around on that 300 degree surface. So now I'm going to fill this guy up, and I'm going to do it a little bit above the track because I want it to not be in touch with the magnets when it goes superconducting. You have to, if you're wearing running shoes and you spill a lot of nitrogen on the floor, you can freeze the soles of your trainers, your sneakers, and then when you walk away they crack, and then you got to go and buy a new pair of trainers. So.
I took out a baseboard throwing it on the ground once there because it just thermally cracked. It's expanded. Also got it down my shoe before, and that was unpleasant. It's the only injury I've had with it.
So you can see that as it's cooling down, it's boiling really vigorously. As it's cooling down, the superconductor is boiling really vigorously. But eventually, you get to the point where it stops boiling quite so vigorously. It never completely stops because it's in contact with room temperature, but for the most part, it will. And that's the point when we know that these superconductors are now close to 77, probably well below their 93 Kelvin transition temperatures. So what's going to happen then is when I take this plate underneath away, the superconductors, because they're in the magnetic field of these magnets, they're generating this diamagnetic effect, right? So they're producing their own fields that exactly cancels the field they're applied to. So that means that they're repelling the magnets, and it's sufficiently strong that it can overcome the force due to gravity that would pull the train back down to the track, and it will float, right? So now we can see that it's completely floating, and then when we give it a push, because it's not in contact with the magnets, there's no friction. There's only a bit of air resistance, and we don't need to do much.
Is it possible?
Keep on going.
Yeah,
It is.
it's only air resistance basically.
Air resistance.
That's going to
If you
slowly
had this in a
slow it
vacuum,
down.
would it go on forever?
Yeah, I mean
Until like it
In a
gets.
vacuum, in principle.
Newton's first law, right? So an object in motion will carry on in motion.
So like it can go forever until all of the liquid hydrogen.
Yeah, so what we'll
evaporates.
see in a minute is all the liquid nitrogen will evaporate, and then it will warm up, and then it will lose its superconducting properties. I said it's completely reversible. So you can see the track's not quite stable, right? It's a little bit downhill coming around here, and it accelerates, and then it slows up going around there, and eventually it's a bit like a roller coaster, it may not quite make it all the way around.
So can we use this kind of technology to bearing or things like that?
Yes, yeah, exactly. So superconducting bearings are something that people have looked at. Again, the problem is all the cooling that's required to make them work. But those are the sort of things that you would think about for, windmills. So you want to produce really highly efficient windmills. So design an electrical motor that uses superconducting bearings, so there's zero friction. So these things are now floating and able, not using up any of their energy in rotating. So in a minute it will warm up.
Would it be great for like long distance transportation because it reduces?
Yeah. So this is an image here of a maglev train in Japan, and it's not quite the same as this. So in that train, what they do is they build superconducting electromagnets, and those provide the opposing magnetic fields between the track and the train, and so it's not quite